Here's some notes for section 10.3. We might do these mostly in class, but just in case you want to review them, or maybe we won't do them in class. This is the first time, but whatever that case may be, here they are, 10.3. In section 10.3, the things that we are most interested in, there are two. We're interested in infinite geometric series and also in what is called the harmonic series. In the book, this section is titled Infinite Series, but I'm going to be a little more specific because we're specifically interested in these two things. So infinite geometric series, this is a review for you. You have studied these before. The definition of a series is a sum of a list of numbers. So not to be confused with a sequence, right? Sequence just a list. Series is a sum. A geometric series has a constant multiplier to get to each successive term. Right? And we usually call that constant multiplier R. Right? It's like the rate of the sequence, if you want to think of that's what the R stands for. Okay, so here's an example. 1 plus 1/2 plus 1/4 plus 1/8. This is an infinite geometric series. And we would say the first term which we often say that's called A1, the first term, similar to the way we used A's in section 10.1, and that is equal to 1. Right? That's just the first term. And R, the multiplier, how do you get to the next term? We multiply by 1/2. That's all. So you've seen that before. The sum of an infinite geometric series is equal to the first term over 1 minus the multiplier. This is a very important formula. Maybe you remember that, maybe you vaguely remember that, but you need to definitely get that tattooed onto your brain. We're going to use that a lot. That comes up quite a bit. And if you want a short proof of that, so let's let S equal the geometric series. I'm going to leave a little bit of space here. So the first term, A sub 1, plus the second term would be A sub 1 times R, right? Whatever the A sub, you could call it A sub 2, but that's going to be too many letters for me to deal with. So I know that the definition of a geometric series, to get to the second term, I multiply by R, right? And then to get to the next term after that, I have to multiply by R again, and so on, right off the page. right? And then, if you want to, you could take this equation and multiply by r on both sides. So on this side, that would give you s times r equals, and then on the other side, I would get a1 times r1, which I'm going to write here just to line things up, plus a1 r2 plus a1 r3 dot 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 going off to infinity. And then I'm going to subtract, I'm going to take this equation here and subtract this one. So on this side I get s minus s times r. And on this side I get a sub 1, and everything else cancels off to infinity. And if you're thinking, no, that not quite, McGrath, this there's one extra one here. No, there is not, because they're going off to infinity. So there is no term that shows up here that does not also show up here, and vice versa. So if you don't like that, then you're in good company. The Greeks, who gave us a lot of what we know about geometry, really couldn't handle this infinity stuff, but you can handle it. So you factor the s out here, you get 1 minus r, and you solve here, and there it is. Boom. So there's a quick proof of that. You need to know how to write these infinite series in sigma notation. So, for example, our series 1 plus 1/2 plus 1/4 plus yada 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 is equal to the sum. This is exactly the same as in section 10.1. We're just trying to come up with a way of writing what the terms are. So let's see. We could say this is, and I've seen sometimes we write these with n's and sometimes we use k's. So I'm going to do it just for fun. I'm going to use k in here. Let's see. So the first term is, we've seen this one before. It was 1 over 2 to the k, and if you want it to be k, then you could start at 0, right? Or you could do k minus 1 and start at 1, right? So that's a nice compact way of writing this. So all the things we did in the last section, we could do in this one, right? Just taking a list and identifying what's going on and repackaging it like that. All right. So how about this? We'll do a quick example. Write the first 4 terms of the series, use n this time, n equals 1 to infinity of 2 to the n plus 2 over 3 to the n minus 1. And then find the sum. All right, so let's see. If I plug 1 into this, that's 2 to the 3rd over 3 to the 0, plus, if I plug 2 in, I get 2 to the 4th over 3 to the 1. And then you could keep looking back here, but maybe you can see what's happening. We're just multiplying by 2 on the top and 3 on the bottom, right? So multiply by 2 on the top, 3 on the bottom, multiply by 2 on the top, 3 on the bottom, and so on. Right, so there's the first 4 terms. And then the sum is equal to the first term over 1 minus, what was I multiplying by each time? I was multiplying by 2/3. So that's 8 over 1/3, which is 24. So all those infinitely many numbers adds up to 24. If it's troubling to you that infinitely many things could add up to something finite, then remember, you've kind of bought into this because infinitely many rectangles add up to a finite area when we're doing Riemann sums. We know that that's true. Everything of the limit of a Riemann sum and how that's equal to a definite integral. But just in case you want more convincing, here's the series 1/2 plus 1/4 plus 1/8, similar to one that we just did. But I'm going to present to you here a geometric argument for why this is equal to 1. So the first term here is 1/2 over 1. What am I multiplying by each time? Multiplying by 1/2, so that's 1/2 over 1/2. That's equal to 1. So here's a geometric argument for that. What's the area of half this 1 by 1 square? 1/2. What's the area of half of this triangle? Well, it's half of that, so it's 1/4. And then the area of this piece would be 1/8. And then the area of this piece would be 1/16. And then the area of this piece would be 1/32. And then this piece would be, and so on and so on. And that process never ends. You never get outside the square. And eventually you get further and further in there, and if you go ... you let yourself go off to infinity, then you fill in the square, and you get the area of the square, which is 1. So there's one little geometric argument. For that, I mean, that doesn't always work. There isn't a geometric argument for every single geometric series. But that's a nice one to help us understand what's going on. Let's see. What else do I need to tell you about these? An alternating sequence series, excuse me, I do that sometimes. You got to call me on that if you catch me. An alternating series has a r that's less than 0, negative r. For example, the series, how about 1 minus 3/4 plus 9/16 minus 27 over 32, etc. That's an alternating series. Let's try to write it in sigma notation. So using n, it looks like on the top I'm multiplying by 3. On the bottom I'm multiplying by, oh, am I multiplying by 4? Whoops, that should be a 64 then. Sorry about that. And on the bottom I'm multiplying by 4. So let's see, if I started at 1, then this needs to be 1 over 1. So that's 3 to the n minus 1, 4 to the n minus 1, like that. How do I get the signs to switch? Well, if I put a negative 1 to the n power here, then if you raise negative 1 to the first, second, third, fourth, then every time it's raised to an even power, it'll be positive. Every time it's raised to an odd power, it'll be negative, which is exactly what we want. So just have to check and see the first term. If I plug in 1, negative 1 to the n would be negative, but I want the first term to be positive. So I can just fix that by doing that. And now when I plug in the first term, that'll be negative 1 to the 2. So that'll be the first positive term. The next one will be negative 1 to the 3, and that'll be negative. And that gives me what I want. And then to find the sum of this, that's the first term over 1 minus the multiplier here. I'm multiplying by negative 3/4. So be careful there. So that's 1 plus 3/4, or 7/4, and 1 over that is 4/7. So that all adds up to 4/7. Right. All right. Now, one of the most important series, I think probably the most important infinite series that's not a geometric series, and maybe the most important of all, is the so-called harmonic series. And the harmonic series is the sum from n equals 1 to infinity 1 over n. In other words, just the reciprocals of the natural numbers. This series does not converge. The harmonic series diverges. That means if you try to add up all these things, it crawls off at the most tragic pace, crawls off to infinity. It's pretty easy to prove this, and the proof has been known for a very long time. But the harmonic series diverges, and here's the easiest way to show that it does. 1 plus 1/2 plus third plus 1/4 plus, now I'm going to start skipping some terms here. It doesn't mean I'm leaving them out. I'm just, for the sake of what I'm going to show you, I'm just not writing them all down to save some space and not lose my mind in showing you this. Okay, so there's a whole bunch of terms, this sequence. Well, this one here is just equal to 1. This here is equal to 1/2. Now if I group these two terms together, there's 1/4 plus a number, I mean these are getting smaller, so if I go backwards I'm getting bigger. So this is 1/4 plus something that's bigger than 1/4. So whatever this is, it's greater than 2 1/4s, right? Because this is a 1/4 and this is something that's bigger than 1/4. So you add those together, it's bigger than 2 1/4s. So I get something here that's greater than 1/2. Then if I group these four together, I have 1/8, and then I've got 3 other terms that are all bigger than 1/8. So I've got 4 things that are at least as big as 1/8. So that's greater than 1/2. If I group the next 8 terms together, I've got 1/16, and then I also have 7 other terms that are at least as big as that, right? So the sum of these 8 terms has got to be greater than 8/16, or 1/2. And then if I group the next 16 terms together, I think you're getting the idea here, right? I got 16 terms that are all each either equal to 1/32 or bigger than that. So go so on and so on. And there is no end to this process. So that means as I go through and add up all these terms, I can get as big as I want. You can go off, you can make this thing equal to 1,000,000. You have to go really, really far out in the series to do that. But however big you want this sum to be, you just have to keep going, and you can add up 1/2 at a time just by doubling the number of terms you collect together. So there you go. This series diverges, but boy does it does so at a very tragic pace, and we'll learn in the next few sections that this harmonic series is sort of a line in the sand between series that do converge and series that don't converge. And we'll have to learn a little bit more about what we can do with series to be able to prove that, right? But here it is. This is a very elegant little proof that does not require any calculus or anything of how and why the harmonic series diverges. And I think that's all you need to know from this section. So there you go.